Welcome to my home again. This is another lecture for ATMO 412. How is everybody doing? Are you doing well? Are you staying inside? I've been staying inside for the past few weeks. It's not great, but it's okay. There's nothing else we can do. Actually, I wanted to share this funny thing that happened to me. I got an email a couple of days ago from some colleagues who invited me to a workshop. And the workshop is going to take place in December. And when I read the invitation, I thought, wow, there will be a December. Like, there will be a future at some point. Even though we seem stuck in this, I don't know, grand finale of the world, there will be an after this virus. There will be some kind of a return to normality. And it kind of reminded me of the conversations I had when I was a kid with my great aunt. Now, I grew up without grandparents. They were dead before I was born, and great aunt was really the closest thing to a grandma that I ever had. She was born in the 20s, and as you can imagine, I was a curious kid, and so I always bombarded her with questions about what it was like to grow up in the 20s and 30s, what was fascist Italy like? What was the war like? And there were a lot of things that she told me that made no sense to me. Like, I remember one of the questions that I kept asking her was, how could people go about their daily life during World War II in our villages, knowing that people were dying every day at the front? Like, how could you keep doing mundane things in the face of all the devastation and all the death? And she would give me some answer like, well, at some point you just got used to it, or, well, you just did, or something like that. And it never made sense to me. Like, great on that. It's impossible. Like, how? So this past week in Italy, something between 700 and 1,000 people died every day because of the virus. And yet, last night, I found myself watching YouTube videos of people whispering into microphones. And I thought of that, and I thought, wow, I get it now. Like, I think I get it, great aunt. Yeah, people learn to go on with their lives somehow. There was another question that I was thinking about that I wish I asked her, but somehow I never did, and I kind of regret not doing so. And the question was, what was the first thing that you did, great aunt, right after the war ended? I remember she told me stories of when American tanks were coming into the village and the Nazis left our village. There was some drama because some person from the village made fun of the Nazis and they shot him. But the Americans came, and it was, this great joy, the liberation. But I never asked her what she did. What was that one thing that she had been dying to do and that she could finally do? Great aunt unfortunately passed away a few years ago, so I cannot ask her this question. But I thought to myself, what am I going to do? When the virus will be over, when the pandemic will be over, what will I do? Now, I found an answer for myself. I'll not share it with you because I don't think I could go through the answer without breaking down into tears. So let's spare each other, the beautiful spectacle of me crying in front of a webcam in an otherwise empty room. But I'll put it to you, what would you do? As an exercise in optimism, what would you do when this pandemic will be over? What is the first thing that you will do when we will go back to some form of, I don't know, normality? If there will ever be, some kind of normality in the following months. So, anyway, this having said, after these few minutes of me rambling, because, well, I haven't seen a single person in a week, and so I kind of felt the need to talk. Let's get started. today we will have, today's topic will be a beautiful subject. We will talk about baroclinic instability. Today's lecture will be a little shorter, but it's a very dense lecture. So even though there aren't going to be as many slides as other lectures, this will be, the material will be a little challenging. I believe that you'll see this material in other classes, like Fei-Fei's class. And so I will not go into too much detail of the math, but I invite you to look at the textbook, at the details. And if you have some questions that I did not cover, or, some doubts or things that aren't clear, please feel free to Skype me, Zoom me, or write me if there is anything. So baroclinic instability. First of all, I can get started. What is an instability? We have some kind of general understanding of what an instability may be just from daily life. But in physics, we talk about instability whenever we have some dynamical system, and the dynamical system is such that small perturbations can grow spontaneously, potentially indefinitely. Okay, so even small perturbation to the system. So an example of instability is if you take some kind of a bowl and you turn it around, and on top of the bowl you put a little ball. Okay, and you can put the ball in balance at the very top of the bowl, but if you touch the ball ever so slightly, the ball is just going to fall down. Okay, or if you try to, there was this thing going on the internet where people were putting their brooms standing or something like that. That may be an example of an instability that you may be able to find the equilibrium of a system like that, but if you move the broom ever so slightly, it's just going to fall down. Okay, and so this is what we mean in physics when we talk about instability. In atmospheric sciences, clearly there are many examples of instability. There's upright instability, slantwise instability. There's Kelvin-Helmholtz instability. This is a really hard word to pronounce unless you're German. Helmholtz. And there is barotropic instability, and finally there's also baroclinic instability, which is what we will talk about. Barotropic instability is an instability that happens whenever you are able to extract energy from a background flow. We saw this when we talked about the jet stream. If you are capable of extracting some kinetic energy from the jet stream and pass it to some eddy in the atmosphere, and you can make the eddy grow, that's an example of barotropic instability. Baroclinic instability means that the energy is not coming from the kinetic energy in the background flow, but instead it's coming from the potential energy of the base state. This is relevant for us because last time we talked about France. A couple of classes ago, we talked about extratropical cyclones. And if you remember when we talked about the history of extratropical cyclones, we try to understand cyclogenesis, meaning how these cyclones are formed. And there was sort of an early theory by the Bergen school, where essentially you had to have, so the idea was to have fronts passing by, and the fronts would then amplify and lead to the cyclones. But the theory that was put together by the Bergen school was not effective at predicting everything. And so it was only with the work of people like Charney and Eadie later that it was shown that it is possible to have some kind of an instability that would then grow spontaneously into the cyclone. The question that we had left open when we talked about cyclones was certainly how do cyclones form, but also if you remember, we saw that oftentimes we had an upper level wave coming by, and this wave sort of increased existing vorticity and led to the generation of the cyclone. So how did this wave come about? What are the reasons why we have these waves and these waves grow? So we could even go in a very sort of dramatic setting where we get rid of topography of every feature on the Earth, and we just have a very simple Earth that is covered by the ocean. Okay, so if we get rid of all that, would we still observe extratropical cyclones to be formed? Because as it is right now, it could be that topography maybe plays a role. Remember that we said on the leeward side of mountain ranges, often you have an increase in vorticity, in the relative vorticity, and so maybe mountains have something to do with extratropical cyclones. So remove everything, okay? Could you still have these waves forming? If you look at the pictures in this slide, there are these are two different areas of the U.S. The picture on the left, if you look at the geographical contours, this is the East Coast, more or less, and the picture on the right, it's something, you can see Alaska, you can see the Aleutian Islands, which is this kind of a necklace of islands, and Russia, which you may or may not be able to see from Alaska, depending on who you ask. But and so you can see that you have two different kinds of patterns, if you will. In one case, the case on the left, you have just one very smooth wave. Continuous blue lines are 500 millibar geopotential heights in both figures, and the shading is vorticity, cyclonic vorticity. So in one case you have this very smooth wave. In the other case, you have you have one large wave, but you also have a lot of shorter waves embedded in the larger wave. Okay. So a good question is, what sets the scale of these waves? Is it, I don't know, has the Rockies anything to do with it? Or could you have different waves of different scales, even in a perfectly smooth planet? Now, all these questions are excellent questions, obviously, but we're not going to be able to solve them until we have a solid theoretical framework to do this. And this is exactly what Eadie and Charney provided in the 40s, more or less, of the past century. So, as we were saying earlier, the Bergen School was all for fronts. There's a front, and the front increases the vorticity, and it's kind of responsible for the cyclones. But their answers didn't really quite match with the observations, and so there was a little bit of skepticism as to their findings. It was later, through the work of Eadie and Charney, that it was shown that actually no pre-existing fronts are needed. You don't need pre-existing conditions. You can have some instability grow from very, very little, sort of spontaneously grow from the microscopical scale, if you will. Fronts, instead, were shown to be a consequence of the growth of these instabilities rather than the cause. Okay. Very good. So today we'll talk about the essentially what is called the Eadie problem. In physics or in math, it's traditional to pick some guy's name and put the word problem after it when we talk about sort of solution of some kind of a differential equation type of system. Like the Cauchy problem is given an ordinary differential equation and some kind of boundary conditions, can we find a solution and something like that. So the ED problem is kind of this idea. Make everything super smooth, super zonal and super smooth, or as smooth as you can in an atmosphere. Get rid of topography, friction, whatever. Can we grow instabilities? Can we show that there are instabilities that grow? So the starting point for the ED problem is that first of all, we assume Boussinesq approximation. Do we all remember what Boussinesq approximation is? Boussinesq approximation is that essentially we're kind of neglecting density variations, except insofar as density influences buoyancy, if you will. So horizontal scale variations, we don't really care that much. We can consider density to be some kind of a rho zero constant value, and we'll only consider density because it affects the buoyancy, vertical motions. Okay, that's sort of the gist of the Boussinesq approximation. We'll consider the F plane. Excuse me. So, this means that we are going to place ourselves at some kind of a latitude, and we will assume that the Earth is flat at that latitude in a way. Okay. And then we assume a basic state that is pretty simple, and it's described by the equations on the slide. So we have a zonal flow given by capital U, which is a function of height and of the meridional coordinate. We will not have a base meridional flow, base state meridional flow. We will not have large-scale vertical velocity. We can still, and we will have fluctuations in the meridional direction and the vertical direction, but it's not a major flow, if you will. We assume there's some kind of a jet stream traveling zonally, but no Hadley circulation, whatever. This zonal flow is related to pressure gradients by the second equation. We will assume some kind of a thermal structure that is uniform zonally, can vary meridionally, can vary with height, obviously, but it will not vary zonally. Assume hydrostatic approximation as well, because why not? We will, for now, we will neglect diabatic heating processes. And finally, we will assume that things like density, pressure, specific volume depend on the meridional component, on the meridional direction and the vertical direction, but have no zonal direction, no zonal component. So they're uniform in the zonal direction. Now, these are extremely restrictive assumptions. The atmosphere does not look like this at all, but this is what you do typically in physics and in math. Simplify as much as you can just so that you can get to the core of the problem, okay? So if you start with these assumptions, you can, go through all the steps. The book is great at going through all the steps. I don't think that the point of this class is to learn all the steps, is to know all the math necessarily, but it's more to try to give you some physical understanding of what all this means. So I would strongly encourage you to look at the steps very, very carefully and let me know if there's something that you don't understand. But as far as this class is concerned, don't lose your sleep over this, okay? And so we can start with, we do all the derivations, and essentially starting from the assumptions and sort of the base state that we defined in the previous slide, let's write down the QG equations for this adiabatic, frictionless, hydrostatic, F-plane, Boussinesq type system, okay? And if you do, the equations are the ones on the slide. They look complicated, but trust me, They could be worse, conceivably. They're okay. It's something that you could always feed to a machine, and the machine would be happy to do it. But it turns out that there are some more simplifications that we can do. So let's think about this a little bit more carefully. We will assume a very simple domain. We will assume, because why not, right? Why assume a complicated domain? We will assume a kind of a I don't know what's the word in 3D, but some kind of a rectangular domain, except in 3D. Okay, the word is escaping my brain, but anyway, very simple domain. We'll have a zonal direction. We will assume periodic boundary condition in the zonal direction. Now, periodic boundary conditions, those of you who played Pac-Man, that's exactly what periodic boundary conditions are. If you go out from one side, you come in the other on the other side with no changes whatsoever. We will assume a rigid lid on top at height h, and we will assume that the meridional direction is infinite. We will assume no boundary. Periodic conditions, in a way, you could think of them as joined. And so it will be like taking this rectangle that you see on the slide and kind of deforming it into an annulus. Okay. It's a bit like Pac-Man was actually played on a torus, but it'll be a bit complicated to show that in like arcade video games. And so anyway, we'll assume very simple boundary conditions. Also, we will make some further assumptions about the zonal wind, and we will assume a very simple jet-like structure where wind shear increases. Well, there will be a wind shear, some kind of a constant wind shear, and this means that the wind increases linearly, going from the surface all the way up to the top of the lid, which is okay. Is a good first order approximation, if you will. And we are assuming that the shear is not dependent on y. And so this makes y kind of not useless, but it's as if it didn't really matter where you are in y. And so this is also going to say something about what kind of motions you can have in the meridional direction. Because of the thermal wind relation, we can also show that this constraint that we put on the wind has to be reflected on the buoyancy. And specifically, the buoyancy changes not zonally, but meridionally. And write down the thermal wind equation to verify yourself that this is the only way that things would work. Now, here I've written buoyancy, but remember that buoyancy, in a certain way, buoyancy is temperature in a way, or buoyancy is temperature variations, if you will. So buoyancy and temperatures, which is what comes into play in the thermal wind relation, they're actually kind of the same thing. Modulo some constants, they're actually the same thing. And finally, same thing for geostrophic string functions. The geostrophic string function, given the restriction that we put on the wind shear and on the buoyancy, geostrophic string function can only be, something that depends linearly on y and z, as shown on the slide. Excellent. So the next thing that we do, and I just want to give you a little bit of the gist of the steps. Again, you don't have to memorize all these equations. The next thing that we do is we separate horizontal and vertical motions into two components. We separate them into a basic state and some fluctuations around this basic state, this base state. And also, at least for the horizontal motions, we will separate them into geostrophic and ageostrophic components. Okay. Now, the base state, we're assuming some geostrophic wind, and so there is no base state ageostrophic component, but there's no reason why there shouldn't be some fluctuation ageostrophic component. Fluctuations usually are represented with a prime, and so when we say U prime and V prime in this lecture, we will typically mean fluctuations. And also, if you remember, we didn't go through the derivation of this, but if you remember, at the very beginning when we talked about potential vorticity, we also said there is such a thing as quasi-geostrophic potential vorticity. And quasi-geostrophic potential vorticity, you can still write it down with the assumptions that we gave, and it has the form that you can find on the slide. Now, you see that this is really what we care about, because while the base state is what it is, it doesn't change. And so because we've separated we've separated base state and fluctuations, we care about the behavior of the fluctuation. And in particular, because we are interested in instabilities cannot be part of the base state by definition, because the base state has to stay what it is. Otherwise, it wouldn't be a base state, right? But fluctuations can grow into instabilities. And so we are looking at the equations of the fluctuations because we are hoping that out of them, we will be able to find the instabilities, okay? And the equations for the instabilities, we have 4 equations. The equations for the fluctuations, we have 4 equations. Now, if you count the number of unknowns in this equation, we actually have 5 unknowns. So 5 unknowns, 4 equations. We're not going to be able to solve it, are we? However, remember that the fluctuations fluctuations still obey relations like thermal wind relationship and the sort of geostrophic definition. The fluctuation of the geostrophic component is related. The fluctuation of the geostrophic function is still related to the fluctuation of the wind in a similar way as the base state geostrophic function is related to the base state velocity. Okay, and so these relationships essentially tie together. In this case, geostrophic function or fluctuation, phi prime with v prime. Spare me having to repeat fluctuation every other word. And phi prime with b prime. So we can get rid of some variables and simplify the system a little bit. And so now we have a system of equations that in principle is solvable. In principle, we can solve the equations above and find the solution, okay? Before we do that, and before we actually talk about the real solution of the ED problem, which we've been talking about for 23 minutes now, we'll take a few more minutes to talk about energetics related to the ED problem. Now, remember that when we talked about QG, we talked about eddy kinetic energy, QG, eddy kinetic energy, and so forth. And we're still interested in discussing energetics related to the ED problem. Excuse me. I try to drink because last time I recorded the lecture, I didn't drink, and because it was kind of rehearsed a few times, I ended up talking for 3 hours in front of this webcam. And at the end of the day, I got a sore throat, and I may or may not have panicked that I had coronavirus for a few days, and I am fine. Although I measure my body temperature way more than I usually do, and so I will keep I'll keep my throat well hydrated this time, because I don't want to spend the next few days freaking out again that I have the coronavirus. So anyway, so a little bit of energetics. Much like we defined a kinetic energy and a potential energy associated with QG, also in this simplified system, we can define kinetic energy and a potential energy. Kinetic energy is obviously going to be related to fluctuations of the velocity, and in particular the square of the fluctuations. And because in our system U prime is 0, given the assumptions that we have, the sort of the no meridional dependence, one can show that U prime is 0, and so we only have V prime. And the potential energy can be defined as essentially the square of buoyancy perturbations. You can put all these things together and show that the evolution of the total energy, sort of the sum of the potential and kinetic energy, is given by essentially 3 terms, which are kind of reminiscent of what we saw when we talked about QG. In particular, there are 2 terms that are pretty interesting. So there's one term that relates buoyancy and vertical velocity, fluctuations of buoyancy and vertical velocity. You could think of this as sort of the vertical flux of buoyancy in a way. And this is related essentially, so this is related to a conversion between the potential and the kinetic energy, okay? And the second term that is interesting is one that comes from the first term on the right-hand side, the VG prime, B prime. And you can show that this is equal to the double integral. This term that we're considering is proportional to d phi prime dx, d phi prime dz. And this is a conversion from the base state available potential energy to the eddy potential energy in the system, okay? So I like this equation because it kind of contains all the basic terms that we need to understand how energy is extracted from the base state, from the available potential energy in the base state. And then it's transferred to eddy potential energy, and then how eddy potential energy is converted into eddy kinetic energy, which is ultimately, what your disturbance would have, right? You want something that is first capable of growing, but then you kind of want it growing, if that makes sense. And also, we can still have an ageostrophic motion, much like we had it in when we talked about QG, right? When we talked about Franz, you remember we defined an ageostrophic string function, okay, and we defined it in terms of U prime, ageostrophic, and W prime or omega prime, and we can do the same here because we will still have potentially an ageostrophic component and we still have some vertical motion. And you can still, you can crank this definition into the equations and you can show that this string function has a very similar form to the one that we saw when we talked about atmospheric fronts. And in particular, much like when we talked about fronts, this ageostrophic string function depends or is quote unquote forced. Well, I don't like the word forced here, but it depends on the zonal component of the Q vector. So if you remember, that was exactly what happened when we talked about ageostrophic circulations associated with fronts. Okay, so this was pretty much what I had to say about sort of the preliminary material. Now we can talk about the solution to the ED problem. Now, let's talk math for a little bit. What does it mean to find some instability? Like, how do you show that something is unstable? Now, what you could do is you take the equations I gave you a few slides ago, and you give them some initial condition, and you integrate them, and you show that that becomes some kind of a cyclone. Great. But, that will sort of depend on the boundary conditions, and, how do you pick boundary? It's hard. So something that is slightly more general, actually something that is more general and that we could do is that we look for so-called normal modes, okay? I don't know how many of you remember Fourier analysis and Fourier series. I hope many, but in case you don't remember that, in the 19th century, Fourier essentially showed that well-behaved functions could be represented as the sum of waves, okay? Periodic functions, or functions defined over an interval, you can show that they could be written down as sums of sines and cosines, infinite sums of sines and cosines. You could think of that almost as if we were dealing with vectors. When you have a vector, you can represent the vector in many different bases, right? You could represent it in XYZ base. You could represent it, you can turn around the axes, you can stretch them and move them about. So you can change the bases. The vector remains the same, but you represent it differently, okay? If you rotate the axis, if you have a vector that is perfectly aligned with the y direction, and then you turn the axis, then the vector will not be aligned with the y direction anymore, and will have components in y and in x directions, right? So this is kind of the idea. Depending on how you pick your basis, your vector, the representation of your vector will look different. Now, Fourier idea was functions behaved very much like vectors. And you can still define different kinds of bases. And in each basis, you can represent your vector, which is a function. Now, the mental gymnastic that you have to do here is that functions can be thought of vectors living in infinite spaces. Okay. Fourier went on and showed that in these infinite spaces, things like sines and cosines represent orthogonal vectors. And so they'll be perfect to represent a basis. That would be like a natural way to represent a basis. Are there other examples of orthogonal functions? There's a way to make the notion of orthogonal function precise, but we'll not get into the details. But is there a way to make this notion, is there a way to generalize? Are there other orthogonal functions? Yes, of course. Yeah. Are they more complicated than sines and cosines? Well, yeah. So let's stick to sines and cosines for now. In particular, you remember we had talked about how exponential of imaginary numbers are sums of cosines and sines. And so these exponentials, e to the ix, are the natural, almost like a natural basis for orthogonal functions, if you will. Okay. So just think about this exponential function, e to the ix, okay? And so far, we're assuming that x is real. And so e to the ix, you can write it as cosine of x plus I sine of x, which is equation 7.94 on the textbook. And so these are just waves, right? However, what happens if x is complex. So it has a real part, but it also has an imaginary part. If it has an imaginary part, the imaginary part multiplied by the I in front of the x will give you a real number. And so we start with complex exponentials, and we say if the complex exponential is only imaginary, you're just going to oscillate, and that's that, And sums of these oscillations will give you some functional shape, which is something in the atmosphere. However, if the argument or the exponential is not only imaginary, but it is also real, it could have an e to the I x, which is now something that could grow over time. E to the I x t could grow over time instead of just continuing to oscillate. Okay. So imagine that you can write your solution as an infinite sum of exponentials that have imaginary parts and real parts. If we were to care for all of them, then it would be like solving the differential equations. Very complicated. We don't have time for that. And, you'll have to, make some assumptions on how you sum things together. I don't care. Not interested in that. However, the clever thing to do here is to realize that if some of these functions in the sums have real parts, these are going to grow and you're going to have an instability, and we're happy. However, if you just take the one function out of the infinite ones that is growing at the fastest rate, by definition, this will dominate in the growth. So at some point, it'll take over. And it will become sort of the most important component in this infinite sum and series. And so whenever you are dealing with a dynamical system and you're looking for instability, this is what you do. Assume that you can write it as a sum of sines and cosines, which means sines of complex exponentials. Then look at these exponentials and look for the one that has the fastest growing rate, so the fastest real part, if you will. That will be the one dominating the growth. And you can focus on that and study the properties of that. And this is the advantage, that you don't have to deal with boundary conditions because you're not combining all these terms together to form a solution. You don't care about a solution. You're just looking at growth rate. And you can do that with pencil and paper, kind of. Pencil and paper, a lot of paper and a lot of time. So this is just what we're going to do. This is called normal modes because we are assuming that we can, much like any oscillation, you can break it down in different modes. We are assuming that we can break down the solution in many modes. We'll see at the end that one could criticize that. Okay, so we will focus on the geostrophic function for now. Let me drink again. We'll focus on the geostrophic function for now, phi prime, and in particular on the equation related to the geostrophic function that we saw earlier. And we will assume that phi prime looks like the function that we wrote down on the slide. So we will assume that phi prime has some kind of coefficient that will tell us how big the solution is. Fine, that's great. And then we'll assume some kind of a wave-like shape, e to the k, that multiplies x minus ct. X is the zonal component, t is time, k is the wave number, so it's 2 pi over wavelength. Now, if all the numbers in this form that we're hypothesizing for phi prime is real, then we'll just have a wave, periodic wave with some period with phase speed c and wave number k. If, however, the phase speed c is imaginary or is complex, so it has an imaginary component, the imaginary component, because it contains an I, will multiply the I in front of everything on the exponential, and it will give a minus sign. And so this gives us a chance to find an instability. So if you do some massaging of the equations that we wrote down, and you get to equation 7.100, which is an equation for phi prime, and let me collect my thoughts. Yeah, so now essentially go and write down an equation for phi prime, and in that equation you plug the solution that you expect, so real component of phi hat e to the I k and that will give you some algebraic equation for c. And that's where you then go look for the imaginary component of c. So if you do that, it's a very long process. I will spare you the details. You don't have to learn the details by heart. The solution to this is on the slide is equation 7.115. And the solution depends on hyperbolic cotangent and hyperbolic tangents. Brief aside, you'll notice when you look at all the different steps that now we're talking about hyperbolic sines and hyperbolic cosines. Well, go look at the definition of hyperbolic cosine. Hyperbolic cosine is e to the x plus e to the minus x over 2. And why is hyperbolic cosine showing up in an equation that is supposedly has to do with waves? Well, cosines, if you remember when we discussed complex numbers at the very, very beginning, the cosine was e to the ix plus e to the minus ix over 2. So the cosine of an imaginary number, let's say the cosine of ix, is the hyperbolic cosine of x. So that's why hyperbolic cosines and hyperbolic sines are showing up, on this page. If this sounded obscure, then don't worry about it. I know Joy likes math, so maybe, Joy, you appreciated this. If this sounded cloudy and obscure, do like Men in Black where they were like flashing people with a red thing. This never happened. Okay, so now we find a phase speed which depends on, square root of, all these things. And we introduced a new variable s just to sort of simplify things. And s is a combination of the Brunt-Väisälä frequency, the wave number, h, which is the top of the domain, and f0, which is the Coriolis parameter, right? Now, if c is to have an imaginary component, this you don't need to be Einstein to know that this square root, what is within this square root, better be negative, right? And so either hyperbolic tangent of s is greater than s and hyperbolic cotangent is smaller than s, or vice versa. I'm pretty sure there is no way that you could solve this analytically, so with pencil and paper. But if you plot this stuff and you try to look for solutions where they exist, then you'd find something like what we show in the graph. So on this slide, in this graph, there are three curves. There's y equal to hyperbolic tangent of s, y equal to hyperbolic cotangent of s. Cotangent is the inverse of the tangent, reminder, and I equals to s, okay? X-axis is this s variable that we introduced. And the shaded area, you can show that the shaded area is the region where the product of s minus hyperbolic cotangent s minus hyperbolic tangent s is negative. So this is the region where you have an imaginary component of the C. Notice an interesting thing, that there is a maximum value of S0 beyond which there's no more instabilities in a way. You plug in all the values for N0, H, assuming, some tropopause, F0, and you find that this roughly corresponds at 2,500 kilometers in the mid-latitudes at 45 degrees. This is, beyond this, no chance of getting an instability. But for S smaller, then there is a chance to have an instability, provided that S satisfies these requirements. In particular, you can go even one step further and look for the S that maximizes the phase speed. So you find that one particular wave that has the fastest growth. If you do that, this is shown in on this slide. This depends. The value of X, the value of S that maximizes C is something like 0.8 something, and that corresponds to a particular phase speed. Okay, if you plug in all the values, this corresponds to a wavelength of about 4,000 kilometers, wave number 6 or 7 at 45 degrees latitude. So a wave that has these features will generate an instability that is the fastest growing of all the possible waves. Smaller waves, if you go to 2,500 kilometers, smaller than that, no chance. Okay. And finally, then you can plug things. You can plug these values back into the equation for phi, and essentially find the shape that the amplitude, sort of the vertical structure of this wave would have. And so you can plug, you can plug these values back into the equation for phi and get some equation for the zonal and vertical structure for this solution, essentially. And if you do that, you find a solution that looks like what I'm showing in the slide. The middle panel is the string function, the phi hat z, which was multiplying the e to the ix, ik x minus ct. And this is, it almost looks like the combination of an upper wave and some lower wave. The top panel shows the top disturbance alone, and the bottom panel, shows the bottom disturbance alone. The combination of these two gives the full solution. But it's kind of interesting because it gives you this intuitive understanding that we had the other time, that when we talked about the upper and the lower troposphere somehow combining and conspiring to form, when we talked about the phase locking of upper level and lower level disturbance. So something similar is also happening here, where you have an upper level wave and a lower level wave, and these have the right kind of tilt in a way that they can lock and they can grow and explode into this instability. Notice that these are leaning against the wind shear. Okay. Then you can go on and you can look at the vertical and zonal structure of other functions as well, of other variables as well. So the top panel here, it's still the perturbation. This is not the geostrophic. This is not the string function. The top panel is the geostrophic flow, which I remind you only has a meridional component, perturbation meridional flow. The middle panel is the perturbation temperature, and the bottom panel is the vertical velocity. Notice that perturbation temperature actually has a different tilt compared to everything else. And this means that on the top of the domain, you have warm troughs, and at the bottom, you have cold troughs. So troughs are warm top of the atmosphere and are cold at the bottom of the atmosphere. Another important thing, notice that we have southerly winds are maximized to the west of the trough axis, and they are also am I reading this? Southerly winds are maximized to the east of trough axes and maximized west of ridge axes, which is kind of what we expected from the string function. Also, if you combined the information that we're getting from the perturbation temperature and the meridional component of the flow, we have southerly perturbations have positive temperature perturbation, northerly perturbations negative perturbation in temperature, right? So this means that in total we have a northerly meridional heat flux, which is exactly what you want, because these disturbances in a way arise as a way for the atmosphere to transfer heat to the polar regions, and so you want something like this. And also finally, in line with what we expected, given what we talked about when we discussed extratropical cyclones and QG, ascent in regions of sort of warm regions at the surface, and descent where you have colder temperatures. So the zonal and the meridional structures are kind of perfectly in line with our expectations. Notice also that there is about a 21 degree phase shift between the thermal and the string function fields. And this is important because this is consistent with the mechanism of self-amplification that we introduced when we discussed the phase locking mechanism. The phase locking mechanism that led to the self-amplification of extratropical cyclones. Also, notice that there is a number that we can introduce as the Rossby depth, and this is the Coriolis parameter over Brun-Weissala function frequency over the wave number, so F0 over N0K. And this is kind of a magnitude that guides the likelihood or the potential for a perturbation to grow. And so if the depth of the atmosphere is not is not good, if it's too small compared to the Rossby height, then there's no chance that that instabilities could actually grow. Okay. Also, we have vertical wind shear, right? And so Just remember from the base state that we imposed. And this vertical wind shear means that the upper and the lower edge waves are going to be advected differently, okay? And they're going to be affected by the circulation differently. And so when the waves are too large, so when you have a very, very long wave, advection actually affects their propagation to the point that no self-amplification can happen. So apart from a short wave cutoff that we had discussed, there's also a long wave cutoff because of the different advection that happens. Also, interestingly, if you assume that the tropopause doesn't exist, so if you let the vertical direction go to infinity, then everything kind of vanishes. Then you don't have an instability anymore. Then it is not possible to find an imaginary component of your wave. So all you can have are these long waves that propagate, but nothing grows out of it. This is kind of similar to saying that we're considering, h going to infinity is like saying that we're only considering sort of very small scales in a way of the previous atmosphere. And so this really highlights the importance of having some finite depth in the troposphere, and this depth has, has the right size, if you will. It's not too small, it's not too big, and it can let this, this growth happen, if you will. Notice also that now, if you look at the waves, the top and the bottom plot on this slide, now there's no 21 degree shift anymore. Now everything's perfectly, in phase, kind of. And therefore, again, you don't have the possibility to phase lock like you had before. And to conclude, I just want to talk about this idea of normal modes. This certainly is a way to show that we can have instabilities. Okay, let me drink again. That we have instabilities. But the fact that we can have instabilities this way doesn't mean that all instabilities come from these small scale perturbations that grow. Just because A causes B and you observe B doesn't mean that A is true. It could also be that C causes B. And so when you're observing B, it could be A, sure, but it could also be C. Okay? And this is a typical logical fallacy that many make. And so some have criticized this idea of the normal modes and argued instead that most cyclones in the atmosphere actually grow out of finite perturbations. Here we're assuming infinitesimal perturbations. U prime, phi prime are really, really small, and out of this you get something that gets really big. But some are actually arguing, well, if you trace back all the extratropical cyclones that we observed, some said, well, most of them, or at least many of them, are generated by finite amplitude waves, not infinitesimal waves. And these exist everywhere in the atmosphere for whatever reason. They exist because there are mountains. They exist because, because the world is complicated and complex. Still, though, even though baroclinic instability may not be the reason why we observe all of the disturbances, it can be shown that it's the reason why many disturbances grow. Many disturbances grow and develop in perfect line with what is predicted by the ED model, if you will. And so there is still some validity into having a very simple, but at the same time, a very valid, very solid, theoretical background. So, just keep in mind, as far as theoretical framework go, normal modes are excellent to find some simple solution, but just keep in mind they're not the whole solution to the problem. Okay, I think this completed all that I had to say about baroclinic instability. Now, as I'm sure you'll have noticed, there is no lab for the baroclinic instability, and this is partially to do with the fact that this chapter was really very mathematical and not so much phenomenological like the other chapters have been. And so I think labs and exercises would have been, just a lot of math and solving, the ED problem in different ways and assuming different things. And so there will be no lab associated with this. This will still be part of, quizzes that we're going to do. So this doesn't mean that you can, gleefully ignore all that we talked about over the past hour. But there will be no lab. So this means that next class, we will actually jump to the next topic, which is cold air damming, which is probably going to be a favorite topic for some of you who live on the East Coast, where this happens a lot. Looking at you, Joy, from North Carolina. It certainly seems to be one of the favorite topics of Gary Lackmann, who also lives in North Carolina. But it's a very interesting phenomenon. And so even though it's quite location specific in a way, and it doesn't apply to all the same way that baroclinic instability could apply to the entire planet, it's still important because, mountains exist kind of everywhere. And so it's important to look at that. So no lab. At the end of this lecture, I expect everyone, as you did last time, everyone to send me, please, a written map discussion. Some have asked me if they could experiment with other formats. Someone was asking if they could do a video of them giving the map discussion. By all means. I said written map discussion because that was the simplest way to do it. And so if you want to stick to a written map discussion, that's totally fine. If you want to go crazy and, record yourselves the same way that I'm recording myself inside of my house, by all means, please do it. What else? Please continue to do the weather challenge. Some of you gave me some feedback about the lecture online. Feedback was greatly appreciated. If you have any more suggestions, if there's something I'm doing that is, that is annoying you, or I'm not doing something that you'd like to be seen, please say so, and I'll be more than happy to accommodate your requests. I'm so gonna get a sore throat, and yeah. Paranoia starts in 5, 4, 3. Anyway, please stay inside. As I said the other time, this virus is extremely serious, and things are getting really bad for the US and for Hawaii, and they'll get, you should expect them to get a lot worse. We're all in this together. We're not alone. Call me if you need anything. Still have the pasta here. So just let me know. But yeah, stay inside. Don't go out. Don't go to the beach. Don't do silly things. Self-isolate. Avoid contact as much as possible. And please, please, stay healthy.